Welcome to Taco Tuesday, commercial focus style. Brett Zerba here. And believe it or not, I am in the lovely Newport, Rhode Island. Anyone that's ever done some traveling to Rhode Island or to the Northeast, maybe you've spent some time in Newport, Rhode Island. Taco is having a national sales meeting. So both Rich and I are in Newport, Rhode Island, in different hotel rooms right now for today's presentation. We're missing lunch, but somehow I'm sure we'll find some way to find some food after today's discussion. Taco Thermal Appliance Company, 105-year-old company. I guess I'm doing the math wrong, but pretty amazing, pretty amazing. We are learning some things. Rich and I, our heads are spinning about some of the continued growth that we are experiencing. Matter of fact, tomorrow, all of us from today's session are going to the Taco Fall River facility, our welded products facility, for the grand opening of its addition. Very, very exciting for that, and just a great thing. I think we added over almost 100,000 square feet of additional space with very, very high bays down there, and total length of cranes available. It's phenomenal. I'm not giving it all the justice I should be, but nonetheless, quite the thing. So obviously, I'm going to be moderating today's event. My good friend Rich Medeiros will be the main presenter, and we're going to be talking about hydronic heating plant concept design. All right. So a couple of groundworks here. I'm assuming you're hearing me, because no one's screaming yet, but if a couple people could raise their hands or send in a question saying you are hearing me, please help, please. Anybody? Oh, we can hear you. Thank you, Chano. Oh, appreciate that. I get scared sometimes. You never know with technology when you're on the road, but good, that's great. So again, there is one handout. Please feel free to download that. It's got a lot of rule of thumb calculations and information on there associated with today's presentation. So just keep that in mind. It's a very a neat handout to have in your back pocket as you move forward doing some designs associated with heating situations. And again, 24 hours from from now, you should get an email with access to your certificate, as well as access to the recording, because this is being videotaped, or no, recorded. I shouldn't say videotaped. We're not in front of any cameras or anything like that. So keep that in mind. I will be monitoring the questions, and we will make sure we bring those up when appropriate, or Rich will take a break so we can get something taken care of there. But other than that, I think that's enough yapping from me. I'm going to turn it over to my good friend. Hello from Greece. Hi, Mr. Chris from Greece. Welcome. So what time is it in Greece? It must be 6 hours, 6 p.m. You're having dinner, getting ready for dinner, I would think. So anyways, welcome. Glad you're on. Take it away, Rich. I'm all done yapping.
Well, thanks, Brett. Just a quick check. I'm going to assume you can hear me okay.
I can, that's for sure.
Okay, great. So if the audience for some reason cannot hear me, then they'll be sitting in silence for a while.
Jared says we can hear you. So I'm feeling good, Rich. I'm feeling good.
Excellent. So today's discussion is about a hydronic heating plant, and I want to emphasize this is a concept design. This is the process that you would go through to develop a concept for a heating plant. And Brett and I have done this presentation a few times in the past. It's not a lengthy one, but it does get people thinking about how their heating plant might be conceptualized. So let's get into some of the topics that we're going to be covering. Oops, this is one of those technical things, Brett. When I press the button to change the slide, nothing happens. So let's try it again. There it goes.
There we go.
So one of the things I like to make sure that people are aware of is that they need to review and comply with all local and national codes before starting a heating plant design. That's extremely important because many heating plants And we're going to focus today our attention on fossil fuel type heating plants. There are very specific codes to keep things safe and to keep people safe. So the codes are very, very important and need to be followed closely. So here are some of the things we're going to talk about. I like to start out by saying I want to design a heating plant, but where do I start? What type of fuel should I use? Where do the boilers go and how many do I need? What about primary pumping versus primary secondary pumping? What's that all about? And how many pumps do I need? Where should the air separator be located? Basic system layout. So this is topics that we're going to cover. So like I said a moment ago, I want to design a heating plant. Where do I start? Well, sometimes I actually tell people to start at the beginning. And at the beginning, typically you're starting with the building. This is actually a photograph of the TripAdvisor building located just off of, what is that? It used to be called Route 128, right, Brett? And now I think they reassigned it, but
it still has both numbers associated with it, 128 or 95 north, both heading, well, north-south. You can go north or south on it. And it's located, the town it's located in is Needham, Needham, Massachusetts.
Massachusetts, yeah. So you can see it from the highway, and I only put the picture on the screen here because I kind of like the looks of the building. But we're going to make believe, we're going to pretend that this building has a certain size. I have no idea how big this building is. So we're going to pretend that this building is a simple office building, and it's the TripAdvisor headquarters building. I think it's the headquarters building. For all I know, they built another building somewhere and called it their headquarters building. But this particular one is easily observed from the highway. We're going to pretend that this building is 480,000 square feet. What its actual size is, I have no idea. But it gives us a kind of a picture of what potentially this building might look like and what we might need for a heating source. So let's keep going. A few things here. We said the building was 480,000 square feet, and we want to figure out how much the heating load is. So one way in New England that we estimate the heating load for a building is to assume that the heating load is approximately 30 BTUs per hour per square foot. And I always tell people that, which you'll see, I have a little asterisk here. The heating load then, if you multiply 30 BTUs per hour per square foot times 480,000 square feet, that comes out to approximately 14.4 million BTUs per hour. And you can see that little asterisk after the BTU per hour. And why do I put that there? Because the actual heating load should be based on a detailed heating load calculation. If you still have it, because the TACO load tool was, it resided on your desktop when we had it, right, Brett?
Yes, sir.
But the load tool is no longer available. But for those of you that still have it sitting on your desktop, that was a good, nice little package for estimating the heating and cooling load for a building. The load tool that we used to use does not include domestic hot water. So you have to put in some value for domestic hot water. Now, keep in mind that whatever the actual heating and cooling load calculation methodology that you use, and most people are using software today. Train has a nice program, Carrier has a nice program. There's several independent companies that provide software for heating and cooling load calculations. That's what the building design should be based on. But for conceptual purposes, it's okay to use a rule of thumb about, in this case, about 30 BTUs per square foot, per hour per square foot. Sorry about that. And that gives us a good starting point, rough idea of what we're talking about. All right, so what type of fuel should I use? And let's assume for a moment this is not a building that's going to be electrified. So we could consider using multiple fuels, but we're interested in the cost of the fuel, the heating value of the fuel, how to store the fuel, if the storage is a process that we need to think about. So let's think about natural gas for a moment. I'm sorry, I meant to say, let's think about natural gas, potentially propane, and fuel oil, number 2 fuel oil, or sometimes referred to as light fuel. So what are we talking about here? Well, here's the cost of fuel that I had collected several years ago. And I was looking at the numbers this morning, Brett, and I realized that the cost of fuel has gone up dramatically. I mean, when I did this, natural gas was around 95 cents per therm. Propane was about $2.95 per gallon. And fuel oil was about $2.10 per gallon. And I had looked at fuel oil prices because I heat my home with fuel oil. And I looked at fuel oil prices a couple of weeks ago, and they're up around, they're not super high, but they're up around $2.60 a gallon. So it's a little bit higher than these numbers here, but you'll get the idea by using these numbers here. So Massachusetts, January 11th, 2021, which is about 4 years ago, that's when I got these numbers. So, but you should use whatever numbers are appropriate for your area of the country. And you'll find that in some parts of the United States, especially, natural gas prices can vary dramatically depending on where you were or where you are. I remember talking, Brett, to a gentleman several years ago who was in Oklahoma, and he told me that the cost of natural gas was like 25 cents per therm. I said, that's unbelievably inexpensive.
Yeah. All he had to do was drill down, and he got it.
Well, that's what he said. Just drill a hole in the ground and drop a pipe in the ground, and you can get natural gas. So, well, we're not quite that lucky in New England, so it's a little bit more expensive.
Actually, we were hearing from one of the presentations we sat through yesterday that there's a data center going in. I thought he said Alaska, where that they're because of the energy and the issues with getting energies for all these crazy data centers that are going in. They're going to create it right on site because the natural gas is there. They can just get it.
That's amazing.
I know.
Yeah.
It's unbelievable. Anyway,
I don't know about in your town, Brett, but if you drill a hole in my town, all you get is water.
Same thing.
Same thing. Okay, so let's think a little bit about the heating value of fuels. I put this little chart together. I actually took a picture of this chart online. And if you notice, natural gas is 100,000 BTUs per therm. That's the rule of thumb. And propane is about 92,500 BTUs per gallon. And if we go all the way down to fuel oil, the most popular fuel oil for heating a home is number 2. And that's approximately, you'll see the number that I have here is 138,500 BTUs per gallon. Most people round that off and use 140,000 BTUs per gallon. But if you convert those numbers so that you have an even playing field, you'll see that natural gas is, as indicated, is 95 cents per 100,000 BTUs per hour. Propane adjusted for 100,000 BTUs per hour comes out to $3.19 per gallon. Oh, per 100,000. I'm sorry, per 100,000 BTUs. And look at number 2, fuel oil. There's $1.52 per 100,000 BTUs. So propane is one of those weird things that when I check the price on propane, depending on which month it is, sometimes it's high, like it's indicated here, and other times it's relatively low. And so propane is a popular fuel, but not as popular as natural gas or fuel oil, number 2 fuel oil.
I'm not sure where Steve is located, but he just put a note up. I've been seeing like $1.50 per gallon of propane for commercial. Not sure. Like I said, I'm not sure where he's located, but that's not a
Steve, ask him if he can tell us where he's located at, because propane prices do vary dramatically, like I said.
Vermont.
And that's what they're getting today in Vermont? Wow.
That's what I'm not sure what day he checked, but that's what Steve just said. Yep.
That's great. Okay, so when it comes to different types of fuel, we have to think about fuel storage. So natural gas does not typically have any on-site fuel storage. Whatever is in the pipe is what's available for your heating system in your building. Propane, if we're talking about the amount of fuel that we might consider storing, we might consider storing 55,000 gallons worth of propane. And you'll see where I got this number in a minute here. And let's say number 2 fuel, we would want to store about 41,000 gallons. Now, what we're saying basically is 41,000 gallons of fuel oil would have the same heating capacity as 55,000 gallons of propane. So that's what those numbers are telling us. And I put this note in here, not the tank size. So in other words, propane is 55,600 gallons. That does not mean that you would have to have, that you would select a propane tank of approximately 55 or 60,000 gallons, because the propane has to have a certain amount of surface area so that it evaporates properly to supply the boilers with the right amount of propane. And you get that information by talking to your propane supplier, because based on the amount of storage you want on site, they have a calculation, it's an app that they use to figure out what the size of the tank would be so that the propane creates a certain amount of surface area inside the tank so that it evaporates at the right rate, especially relative to either if the propane tank is buried in the ground, or in some cases it's sitting above ground. So that makes a huge difference on the evaporation rate. So the size of the tank can vary depending on where the tank is physically located, and it could be significant. Fuel oil doesn't have that problem. Fuel oil, whatever the gallons that you store is or that you need is what you would size the tank for, because you're moving the propane, moving the fuel oil using a fuel oil transfer pump. So that's what that's all about. Any other questions, Brett, before we go too much farther?
Yeah, well, I'm going to try to explain this. I'm going to have a little hard time though. Where are we today with the designation for 1,000 BTUs per hour? Is it still 1,000 BTUs per hour equals 1 MBTUH per hour, or 100,000 BTUs per hour equals 1 MBTHU per hour?
Yeah, the abbreviation, people have used it for both, and it's a little confusing. So in general, MBTH means 1,000.
Yes, the M is the Roman numeral for 1,000. Steve just posted.
Yeah,
and
so that's but I've seen people use different terminology. But in general, the rule is MBH, MBHS is thousands of BTUs per hour.
Yeah. Typical.
So here you can see the fuel oil storage. It's if we have 14.4 million BTUs per hour, and we have approximately 138,500 BTUs per gallon, divided by the efficiency of 85%. The efficiency, by the way, could be much higher, especially if you're using condensing boilers. And you'll see that some of the numbers I have here, you have an option of using a conventional boiler or a condensing boilers. And so this would be at 100% capacity for our make-believe building. And if we wanted to have storage for 24 hours times 14 days, it's 2 weeks worth of storage. You would need approximately 41,000 gallons. So hopefully that makes sense to the folks in our audience today. And if they need more input, I'll be happy to provide some additional information. Okay, moving right along. What type of fuel should I use? So when it comes to fuel oil storage, and more specifically, let's focus in on the other items that you would need, especially if you were storing number 2 fuel oil. You would have to have fuel oil transfer pumps, which I mentioned briefly before. You'd have the fuel oil day tank. In many cases, you have to provide a day tank. Some people are providing day tanks and others are not. Now, I prefer a day tank. It makes things much easier to manage. If somebody needs some input into what that's all about, why don't you pop in a question and we'll take the time to answer that. Now you have the fuel oil piping, fuel oil capacity monitoring system. You also have to have a fuel oil leak detection system. And this is where, as I said at the very beginning, where the codes come in, because every community has a different set of criteria for storing fuel oil these days. Basically, the criteria that most municipalities are developing or have developed is basically to keep your eye on the quality of the fuel oil storage system to make sure it's not leaking and going into the subsurface ground and contaminating water supply and stuff. So that's very, very important.
So someone did ask to explain day tanks in a little more greater.
So a day tank is a small tank that usually is in the mechanical room adjacent to the boiler, and that allows you to transfer, sorry about that, fuel from your storage tanks to a small day tank. And again, the size of the day tank is dictated by the local codes. In some cases, the day tank, they don't want it to be much larger than 50 gallons. So consider a small 50-gallon tank inside the mechanical room, and you're using a, usually the boiler itself has a fuel pump on it, and you can pump the fuel from the day tank into the firebox, that the fuel oil transfer pump that's on the boiler itself. And so the day tank has a float mechanism in it, and then it goes up and down to maintain a certain level of fluid, fuel oil in the tank, and it's drawing from the larger, usually storage tank that's either underground if it's in a double wall configuration. Again, this is where the codes come in, because in some municipalities, they don't allow fuel oil storage to be stored underground anymore. It has to be above ground. So hopefully that answered the day tank question.
I'm sure it did.
So what's our fuel choice for this building? My first choice would be natural gas. So I'm going to put a check mark next to natural gas. Partly because propane has the storage issues with it, and it's expensive, generally speaking, compared to other types of fuel. Number two, fuel oil has a whole series of issues associated with it, including higher levels of pollution. So in this particular example, for conceptualizing, I would suggest using natural gas. Now, you can't always use natural gas, because sometimes the simple fact is that natural gas does not exist where your building is going. I looked at a building multiple years ago, was someplace in Maine, and they had no natural gas piping within several miles of the building. So natural gas was not an option for those folks. I'm sorry. Yeah, no, natural gas was not an option. All right. So where do you want to put your boiler plant? Well, you could put it at the top of the building. Usually if it goes in the top of the building, it has, usually it's a penthouse type of arrangement. And it has, there's lots of benefits to putting the heating plant at the top of the building. But one of the drawbacks, again, is fuel, because you have to store it. Usually you're limited to, again, the day tank size, relatively small storage at the boiler itself. And then you'd have to have a fuel oil transfer system. But you have relatively small length of flue for your boiler system. You could potentially put it in the middle of the building. I've seen boiler plants in the middle of the building. It has its own set of ventilation issues. It has to have meet the fire code requirements and life safety and all those other issues. And then probably the most popular place to put a boiler plant is at the bottom of the building. If it's a slab on grade type building, then you're putting it in the slab on grade. And some buildings they have it in the basement. I don't know if you realize this or not, Brett, but our heating plant in Cranston, Rhode Island is actually in a basement. And I think we have
For the
3 to
main,
4
for the
boilers.
main, yeah,
Yeah,
down out by Cranston Street.
yeah, exactly. You have to go down a set of stairs to get to the boiler room. We do have one that's sitting on the first floor, but that's in the opposite end of the building. So that's kind of interesting. We have both in the basement and another one on the first floor. But I have designed buildings in the past where we have put the heating plant in a penthouse. So it's, you know, you can have it almost any way you want. I personally prefer, here it goes, to put it at the bottom of the building. So I would put a check mark. That's where my preference is. So the other thing to consider is the boiler room ventilation and flue determined by code and type of boiler. So again, keep going back to the code issues. So how many boilers do we want? Well, one possibility is to put in one boiler at 100% load capacity. Another possibility is to put in 2 boilers, and you could make those boilers 50% each, or you could consider making them 67% each. So 2 boiler arrangement is a very popular arrangement today. 3 boilers. You could have each boiler at 50%. That implies that you only need to run 2 out of the 3 boilers. Actually, that's our configuration in Cranston. We have 3 boilers in the basement mechanical room, each one sized for 50%, so that at any one given time, if one boiler should be offline, you have 100% capacity. The other option is to have 3 boilers at 33%. So if you lose a boiler, you have roughly 66% capacity. And in terms of heating a building, chances are the peak heating load occurs at night, and it's the worst case scenario. It's the yeah, getting tongue twisted here. Let me take a swig of water, Brett.
Sounds good.
Sounds good. Is that with 3 boilers at 33%, if you lose one boiler, you'd have 66%, and that would allow you to heat the building for roughly 75% of the time. Depending on where you are in the country, if you have a boiler need, that might even be higher. 2/3 of the capacity might provide as high as 90% of the heating hours available. And then there's also the possibility of, let's see, so we put in 50%, yeah, 50% or 33%. My personal choice is the 33%. And the other reason for that is that for 100% capacity, I'd have to run all 3 boilers, but very rarely do I need to have 100% capacity. Generally speaking, I can probably get somewhere between 5, it depends on the building configuration, but somewhere between 5 and 25% of the time I would need 100% capacity, which means at between 75 and 95% of the time I do not need 100% capacity, which means that I have somewhat built-in redundancy. Any questions about the number of boilers or the combination of boilers?
Someone said, why set 67% boiler capacity?
You mean in terms of these 2 guys here?
Yeah.
Having
Yeah.
2 boilers at 67% capacity each? Well, the logic there is that, again, between 75 to 95% of the hours in the year, you're going to have a load that's going to be probably less than 67%. So under those circumstances, which is the majority of hours in the year, your plant becomes 100% standby. And if you're in that range, you know, where it's quite cold out and you're in that upper 10 to 15% of the time where you might need more than 67% capacity, then you have 2 boilers that will be more than enough.
Right.
And by sizing them at 67%, you make the individual boiler more energy efficient. So that's some of the things to think about. Okay, so here is the diagram, and I've got it labeled on the left-hand side here. It's variable primary flow. So in this particular case, every time a boiler fires up, there is a circulating pump that's associated with that boiler. Now, I don't have my pointer tool. Will my cursor work? Yeah, my cursor works. Can you see my cursor, Brett?
I can.
So here we have a dedicated pump serving a boiler. And in this case, the pump would be variable speed, and you would increase or decrease the speed to match the load that's in your building. And in this case, I'm using the same one that I mentioned in a previous slide, where each boiler size for 33%. So as the load increases and decreases, the flow through the boiler increases or decreases. Now, in this particular case, I have not shown a bypass, which may be necessary in order to maintain the minimum flow required by the boiler, which is why I put this nice note down here in the lower left-hand corner, Brett, not for construction.
I already took a picture and sent it to 6 people that were requesting it. So it's already on the web.
So people are already designing the system. This is just for classroom purposes to point out some different configurations of equipment. But you know, you have to do some more thinking about how your boilers are set up with the minimum flow rate required by the manufacturer and whether or not you need a bypass and all of those other things to take into consideration. So yeah, this kind of gives you just a quick snapshot of a variable primary flow system.
Here's a great question. By the way, Syed, who asked about the 67%, patted you on the back and said, great explanation. But Jonathan is asking, do you generally pull through a boiler or push through the boiler with the variable primary flow plant?
Well, you know, it depends on so many different things. My suggestion, again, since this diagram is not for construction, it's not meant to be an absolute representation of how you should do the piping, is to contact your boiler rep and have a discussion with them for the type of boiler that you have as to whether or not you want to have to pump into the boiler or away from the boiler. Generally speaking, you want to pump away from the boiler because that's the expansion tank, in this case, is on the suction side of the pump, but it flows through the boiler first before it gets to the expansion. I'm sorry, it flows through the expansion tank or through the expansion tank point of no pressure change connection before it gets to the boiler. But in general, you'll notice that the air and dirt separator is also on the suction side of the pump and the boiler. So the air separator is at the lowest pressure in the system. Hopefully that helps people with that. All right, so this next one.
How did you come up with 977.1 GPM? I think it was just the software coming up with that, right? Or I don't even see it. Oh, there it is. It's over by the air separator. Oh, by the imposed load.
Yeah, well, in this case, it's a 30-degree differential temperature. If you remember, the total load in the building was 14,400,000.
Yep.
So let's do the test here, Brett. Let's make sure that we didn't mess up when we did this calculation. So it's 14,400,000, 1, 2, 3, divided by 30, divided by 500, and the GPM should come out to 960. Oh, I know why it's 977. The reason it's 977 is because the software does the calculation based on the mass rate of flow in pounds per hour, and then it converts it into gallons per minute when it displays the actual value. So in other words, it adjusts for the expanded water temperature. Does that help?
Excellent answer.
Excellent answer. All right, so we want to go to the next slide here and have this slide shows us the primary, secondary, And if you notice in this case, the primary circuit is associated with the boilers. Those are the 3 pumps and the 3 boilers. This is generally referred to as the primary system. And that's separated by hydraulic separator, which is a Taco 5900 hydraulic separator that separates the primary circuit from the secondary circuit. And then the secondary circuit has redundant pumps for the building load itself. So one of the nice features about primary secondary flow is that generally speaking, when you have a boiler running and a pump, its associated pump running, that pump and boiler combination is at constant flow. And so you don't have to worry about minimum flow through the boiler because it's at constant flow. And in this case, each boiler has a pump that's sized to 322 gallons per minute. That's kind of neat, huh?
Yeah.
Okay. So in this case, I like the primary secondary system. It's sometimes we refer to it as being idiot proof, and it solves a lot of problems. I mean, I will admit that in newer systems, people are considering variable primary flow for their boiler plant, but I prefer the primary secondary flow system. It's much more manageable, and it's easier to maintain, and it's easier to troubleshoot and service. I think that's it. Let's see what we got here. Oh, this is just a summary of all the decisions that we made for the concept design. We decided that we did a very simple load estimate, and we said the building was 30 BTUs per hour per square foot. That came out, multiply that by the square footage, it came out to 14.4 million BTUs per hour. We decided the fuel would be natural gas. The boiler plant location is at the bottom of the building, usually on the first floor, or if there's a basement, usually in the basement. We also decided to have 3 hydronic boilers at 4.8 million BTUs per hour. So that means that each boiler is 33% of the total load. The hot water temperature in this case was 150. With a return water temperature of 120, it's a 30-degree delta T. Because the return temperature is below 130 degrees, this concept design could be a potential candidate for modulating condensing boiler. So that's something to take into consideration. My concept design is not based on condensing boilers, but it could be because you have a low enough return water temperature. I decided on a primary secondary flow for the configuration of the piping system. And the 3 primary hot water pumps, again, would be sized for 33%. Is that all the decisions in this case? Oh, and the secondary hot water pumps are also at 33%. So I believe that that is the summation of all the decisions that were made in order to come up with a conceptual design.
So I have a question, because I do know your background and some of the careers that you've had. Would this be a type of discussion an MEP could expect to have with a potential building owner or whatnot, or architect?
Yeah,
or...
I mean, usually when you're developing a concept of design, you enter the meeting where the owner, and usually it depends if the contractor is on board or not, but the mechanical contractor also has great insight in terms of perhaps the last 40 or 50 boiler installations that they've done, and they've learned a lot about installation and stuff. Anyway, the conversation takes place between the MEP engineer, the architect, the owner, and hopefully the mechanical contractor by then is also on board when you're doing a conceptual design. And you go over these different options and parameters and make your recommendations. And sometimes, people will come back and say, well, I like your recommendation. The concept is valid, but you might want to consider the following modification. Maybe it's a critical facility and they can't have boilers at 33% each. In other words, if they have one boiler goes down, they still need 100% capacity. Usually it's things like hospitals that have those kinds of requirements. But you have a conversation to discuss the pros and cons, and maybe you have to go back and do some life cycle analysis in terms of first cost, operating cost, and potential return on your investment, that sort of thing, or simple payback.
All right, so we do have some good questions. Why did you use a hydraulic separator instead of a bypass/decoupler? I know the answer to that, but I'll let you answer it.
The main reason for indicating that, let me just go back here a couple things so we have the diagram in front of us. The hydraulic separator, and hopefully my cursor is showing that over here, is a pre-engineered product. And for this pipe size, this makes this a very, very simple way of providing primary, secondary hydraulic separation without trying to field design or stick build a bridge out in the field. It takes all the guesswork out of it. So that's the main reason why I chose that as an option.
How do you determine what delta T to use on a system? Great question.
Oh, that's a great question. That also requires some first cost, operating cost analysis, because most heating systems in the past were designed around a 20-degree delta T, which meant that in most cases, the hot water went out to the terminal devices at 180 degrees. Was a pretty common number, and it came back at 160 for a 20-degree delta T. And that meant that the selection for the terminal devices were dependent on a 20-degree delta T with an entering water temperature of 180 degrees. So their capacity for selection purposes was based on those parameters. So if you change your delta T and you lower your supply water temperature, in this case, I went away from sort of the historical approach of 180 degrees to 150 degrees, and then designed the system for 30-degree delta T. That implies that the terminal devices have to be selected for a new entering water temperature. So typically what happens is that in this case, you have to have a significant increase in surface area to get the same BTUs out of your terminal devices that you would with a higher water temperature and a lower delta T. But the benefit, the trade-off is that a 30-degree delta T with 150 supply and 120 return, as I said, it could be a candidate for a condensing boiler. And so now you have a significant energy savings, because condensing boilers can be in excess of 95% efficient, as opposed to a conventional non-condensing boiler, which is they max out at around 85% on a good day, that sort of thing. So that's the decision-making process.
Sounds logical. Dr. Spock, is the use of a condensing boiler driven more by the return temperature or the supply temperature?
Generally speaking, condensing boilers are governed by the supply temperature. The supply water, I'm sorry, I said that backwards.
Yeah.
My brain said one thing and my mouth said another, Brett. Generally speaking, you want to design the condensing boiler based on the return water temperature. And you want the return water temperature to be less than 130 degrees in order to ensure that the boiler is in fact going to operate in a condensing mode. Again, the actual temperatures that make the best sense for a particular boiler configuration should be discussed with your boiler rep in concert with the boiler manufacturer, so that you can make the proper selection for the system that you're trying to design.
Going back to the variable primary design, based on the diagram, it's more important to locate the air. Is it more important to locate the air separator expansion tank at the lowest pressure, not the highest temperature, like in a primary secondary design? Does that make sense?
Well, in general, there's a trade-off, because sometimes it's more convenient to place the air and dirt separator at the higher temperature. It all depends on the relationship between the temperature and the pressure. This is one of those things that you could just as easily locate the air and dirt separator on the discharge side of the boiler. It will operate at a slightly higher pressure, but at a lower, at a higher temperature. So it's up to the individual designer or engineer in terms of what they want to achieve, and sometimes it winds up being physical constraints in terms of how the equipment lines up in the factory, not the factory, but in the boiler room itself.
This is well, I'm going to ask the question. This will be an interesting answer. Do we have a rule of thumb for estimating how much mechanical space might be needed before going through preliminary boiler selections? Oh boy.
No, actually, I don't. And you know, boilers have become much more compact in recent years, and I think it's worth the few extra hours to do the kind of the footprint exercise. But keep in mind that before you decide on how much space things are going to take up, I think you have to make some fundamental decisions based on, you know, the type of fuel like we talked, and the temperatures and the type of terminal devices that you're going to have. Because the amount of space that the boiler plant will take up based on some of the early decisions that you make. In other words, you may need 10% more space in your mechanical room based on the number of boilers that you choose, but you may be giving up efficiency. So that before you go down the road of you know, determining how much physical space you should need, you should try to get your hands around the proper configuration for the number of boilers, percentage of load, temperatures, and, you know, and redundancy.
Someone said that sounds like a question from an architect. How would outdoor air reset controller affect the piping, or does it?
Well, in modern systems, the boiler water temperature is reset based on the outside air temperature. And again, you have to look carefully at the way the boiler is designed to ensure that you're providing a hot water temperature that's both appropriate for the boiler and for the terminal devices in the building. So in our simple example, we have 150-degree supply water temperature. Let's say that the boiler design allows us to vary the supply water temperature from 150. I'm just going to make up a number so you can get an idea of what's talking about. Maybe 20 degrees lower, say from 150 down to 130. And that would be based on an outside air temperature reset. However, that lower temperature may not give you the capacity that you're looking for, you know, on your terminal devices. So it's not quite as simple as a residential reset temperature, because you have so many other variables to take into consideration. For example, in this particular case, we're making water at 150 degrees. And if someone's using that source of water for domestic water through a heat exchanger, domestic water typically wants to be heated up to about 140 degrees. And so if you reset your water temperature too low, then you don't have a high enough temperature to make domestic hot water. So there are a bunch of things to take into consideration before you make your final decision.
Can we have different delta T's for primary, secondary loops?
You can, yeah. You could have a, generally speaking, the secondary loop is going to have a lower delta T than the primary loop.
If you have different ones.
If you want to have a difference, yeah.
Yeah. Any sense to add a drive to the boiler circ to increase the GPM? I mean, most pumps have drives now. Oh no, to the boiler circ. Huh.
Well, again, it depends on the characteristics of the boiler. I've shown this system to indicate that you have variable flow through the boiler. And the boiler manufacturer is going to dictate what that variable flow would be. So in this case, I just said I'm looking for a boiler that can support 322.4 gallons per minute. And that's at 100% capacity for that particular boiler. Okay, so what if the boiler turndown ratio was, I'll use two extremes. Let's say the turndown ratio for the boiler could be down as low as, say, 40%. If your load drops below 40%, then that implies that you'd have to have a bypass to maintain the minimum flow required by the boiler. But if the boiler, let's say, did not have that lower turndown ratio, maybe it only had from 100% down to 60%, then that would have a much different implication of how you configure your pumps and your boilers.
Awesome. Oh boy.
The bottom line is that, you know, the kind of information that we can get you to think about in boiler plant design and conceptual design, it's intended, the presentation that we're doing today is intended to get you to think about all of these different variables and to, you know, contact the appropriate professionals that know about their particular boiler configurations and what makes the most sense, looking at the load, the type of building. In our case, this is a simple office building, but it could be a hospital, for example, which would have a different set of parameters that you may want to consider. So yeah, there are lots of things to talk about. There's no one simple way of doing it. That's part of the fun of doing this type of work, that there's always a variable to be considered.
Given a choice between two locations, highest temperature or lowest pressure, what would you choose for the air separator?
Generally speaking, I like to have the highest temperature.
I agree.
But that's my own personal preference.
Would you use a separate zone with an override to a heat exchanger with the reset controller? That question seems a little wordy.
Yeah, you know, I mean, there's a variety of ways that you can configure things to accomplish a certain task. And so my response to that is that it's possible to do what you're suggesting. You do have to look at the different variables in your system to see which one makes the most sense. I mean, maybe the boiler water temperature wants to be reset so low on an outdoor air temperature reset that makes more sense to have a dedicated boiler for domestic hot water. And again, it depends on the type of system. If you have a hotel, for example, a hotel has a huge demand for domestic hot water as compared to an office building, which has very, very little demand for domestic hot water.
Awesome. We are done.
We are done.
I mean, someone's asking about consideration of buffer tanks and sizing them. We have a nice recommendation on our website for sizing buffer tanks, but I think the best answer to that is check your boiler manufacturer, how much volume of water you need.
Yeah, exactly. I mean, that's why it's so important to work closely with the type of boiler and the configuration of how you want it to operate in the system. Because the boiler manufacturer is going to, like you just said, Brett, they're going to set the parameters for how much volume of water that you're going to need in the system and how big the buffer tank is going to be relative to the rest of the volume of the water in the system.
Awesome, Rich. Great job, my friend.
Well, hopefully everyone got something out of today's discussion. I really enjoyed the questions. They were very thoughtful questions.
A lot of
Get
thank
people
you.
to think about how to put some of the stuff together.
All right. Thank you, Rich, as usual. We have another one in a couple of weeks. Whatever it is, we'll be back. We will be back. But thank you, everybody, for participating. Look for your email tomorrow. If you don't get it, let us know, and we'll follow up on that. And other than that, till next time, hopefully we see you again. Bye, Rich. See you soon.
Take
Bye,
care.
everybody. Thank you very much.